Hello, we are Team 3 and I'm going to explain the exercise 2 of both activities, A and B. Second exercise of activity A. Find the implicit general solution of the following differential equation. 6x y power to 3 plus y sinus of xy plus 1 dx plus 9 x squared y squared plus x sinus of xy dy equal to 0. First, we check the equation to know if it's an exact differential equation. We divided each part with the form my equal to nx. In the first part, we have the derivative respect to y of 6x y power to 3 plus y sinus of xy plus 1, and it's equal to 18x y squared plus xy cosinus of xy plus sinus xy. And in the second part we have the derivative of respect to x of 9x squared y squared plus x sinus of xy equal to 18 xy squared plus xy cosinus of xy plus sinus of xy, and we can see that both derivatives are the same. It means it's an exact differential equation. Then we proceeded to integrate a part of the equation. In this case, we integrate m respect to x, and we obtain 3x squared y power to 3 minus cosinus of xy plus x plus a function respect to y. After that, we divided the integrated solution respect to y and we equalize it to n. Then a part of our result is eliminated in the equation and the derivative of the function respect to y has a value of 0. The derivative function g respect to y is integrated, so we have a 0 and its integral is a constant. Finally, we included the constant in the equation and we obtained the answer 3x squared minus cosinus of xy plus x equal to a constant. Second exercise of activity B. Letter A. Find the integrating factor by inspection and solve the differential equation. X power to minus 2 y power to minus 5 dx plus x power to minus 3 y power to minus 4 dy equal to 0. First, we use the form my equal to nx to check if our equation was exact. In the first part, we have the derivative respect to y of x power to minus 2 multiplied by y power to minus 5. And in the second part, we have the derivative respect to x of x power to minus 3 multiplied by y power to minus 4. Here, both derivatives are different, so it's not an exact differential equation. After that, we observe each exponent of x and y. We choose the smaller exponent of each part of our differential equation to create the integrating factor with positive exponent. Then our equation was multiplied completely by our integrating factor in this case x power to 3 and y power to 5, and we rewrote our equation. Now our differential equation is x dx plus y dy equal to 0. We use the form my equal to nx again to check if our equation was exact. Now both derivatives are the same, so it's an exact differential equation, and we proceeded to solve it. We integrated m respect to x, and we obtained x squared divided by 2 plus a function respect to y. After that, we divided the integrated solution respect to y, and we equalized it to n. X squared divided by 2 is eliminated, and the derivative of the function respect to y is equalized to y because it's the value of n. Here the derivative function g respect to y is integrated, and the result is y squared divided by 2 minus a constant. Finally, we include the function respect to y in the equation, and we obtain the answer x squared divided by 2 plus y squared divided by 2 equal to a constant. Letter B. Find the integrating factor and solve the differential equation x multiplied by tangent of x dx minus y multiplied by cosinus of x dy equal to 0. First, we use the form my equal to nx to check if our equation was exact. In the first part, we have the derivative respect to y of x multiplied by tangent of x, and in the second part, we have the derivative respect to x of minus y multiplied by cosinus of x. Here, both derivatives are different, so it's not an exact differential equation. Then we proceeded to obtain our integrating factor. We obtained two different derivatives of our possible integrating factors, one respect to x and another respect to y. We choose the derivative easier to integrate. In this case, we choose derivative respect to x. We integrated the derivative, and our result is the exponent of an exponential. The answer of our integration is a logarithm. It is removed with the exponential, and we obtain the integrating factor is secant of x. Then our equation was multiplied completely by our integrating factor, in this case secant of x, and we rewrote our equation. In the second part of our equation, cosinus is eliminated with secant of x because both are reciprocal functions. Our new equation is x secant of x multiplied by tangent of x dx minus y dy equal to 0. We use the form my equal to nx again to check if our equation was exact. Now both derivatives are the same, so it's an exact differential equation, and we proceeded to solve it. We integrated by parts m respect to x. We separated the value of u, du, b, and db. Our variable u is equal to x du equal to dx, b equal to secant of x, and db equal to secant of x multiplied by tangent of x dx. We rewrote our integral and we wrote x secant of x minus the integral of secant of x dx, and we obtained the integral is equal to x secant of x minus logarithm of secant of x plus tangent of x plus a function respect to y. After that, we divided the integrated solution respect to y and we equalize it to n. X secant of x and logarithm of secant of x plus tangent of x are eliminated, and the derivative of the function respect to y is equalized to minus y because it's the value of n. Here, the derivative function g respect to y is integrated, and the result is minus y squared divided by 2 minus c. Finally, we included the function respect to y in the equation, and we obtained the answer x multiplied by secant of x minus logarithm of secant of x plus tangent of x minus y squared divided by 2 equal to a constant. That's all, and thank you for your attention.